So let's talk a little bit about ways that we measure pressure, and this is where the units of millimeters and inches comes to be. Okay, this is how we get those terms. So the first device to show you is something called a barometer, and baro just means pressure. So pressure, it's a pressure meter. And the way they construct a barometer is they actually take a glass tube and they fill it completely with mercury, okay? And they take that glass tube and they invert it into a pool of mercury, and this is what happens. The mercury starts out at the very top, and then it falls down, and then eventually it stops. What you have on top is a vacuum. Now, a vacuum really is just a lack of gas molecules. There's no gas molecules present in a vacuum, okay? So there's no gas. And what happens is outside you have the atmospheric pressure, and it's pushing down on all the surface around the surface of the mercury that's exposed to the air, right? And that atmospheric pressure actually stops this liquid from falling. So it turns out this mercury is exerting a pressure of equal, I should say pressure here, I'll call this pressure of the barometer, is equal to the pressure of the atmosphere. And so it goes down that far and then stops. And it turns out if you measure this length from the bottom to the top of the mercury, and it's about one atmosphere. The height of the mercury would be 760 millimeters of mercury, or 29.92 inches. So when we looked at this table before, this is the 29.92 inches. This is the 760 millimeters of mercury. Now, a closely related unit is called the torr, after a guy named Torricelli. And for all practical purposes, these two numbers are the same, although theoretically they're slightly different from each other. All of these values equal 1 atmosphere pressure. So typically atmospheric pressure will support or push up 760 millimeters of mercury. So this is where we get the term 1 atmosphere equals 760 millimeters, and then this is the mercury. You can actually make other types of barometers and not use mercury, but mercury is used by choice because its high density allows the barometer to be less than a meter long. If you made the same barometer out of water, it would be like, I forget, it's like 15 feet high. It's much, much, much taller. Okay, 15 feet? Oh no, maybe 15 meters. Let me do the calculation. Yeah, so I did a quick back the envelope calculation. A barometer made with water would be about 30 feet high. And so, that's bigger than most rooms, or taller than most rooms. And so making them out of mercury allows them to be less than a meter, or less than 3 feet in length. Now, another device to measure pressure is known as a manometer. So in a manometer, we will have a reaction vessel. So this would be the reaction over here. And they're saying high pressure gas, right? But often in a manometer, way it's often used is just to measure the pressure of a gas. And so let's say initially the manometer starts with levels of mercury inside and outside that are the same. There's usually a valve somewhere around here that allows you to equalize the pressure inside and outside. The top of the manometer is open, and so if you turn the valve that's usually around here, you open up the pressure so that the pressure on the inside of the reaction vessel and the pressure on the outside are the same, and when you do that, they come to the same height. So initially the height, we would call it 0 millimeters of mercury, if this was a mercury manometer, and then we close the valve that's up here, so I'll get rid of my little arrow, right? And then we allow the reaction to proceed, and if the reaction produces a gas, then what happens is it pushes one side down, and the other side correspondingly goes up, but the pressure that the gas generates is the difference between the top level of mercury and the bottom level of mercury. Now, let's say the reaction consumed a gas, right? If it consumes a gas, then the pressure on the inside would drop, and then the height here wouldn't be lower, it would be higher, and then this would correspondingly come down because now it's not pushing against as much pressure. But still, the height difference, right, from the top of the liquid to the bottom level of the liquid tells us what the pressure of the gas is in that reaction. Okay, so the last kind of pressure measurement is what we call gauge pressure. And gauge pressure is really like when you measure your bicycle tire pressure, or if you look on the side of a compressed gas cylinder, there'll be a gauge on it, and it'll tell you what the pressure is. And sorry about the annoying animation, but I don't know how to stop it. But that's gauge pressure. And gauge pressure is a little bit different. And the way a gauge actually works is, this is one of those party horn things that you blow into, right? Basically, when you blow into the end, the pressure causes this tube to straighten out. Well, in gauges, a lot of pressure gauges, not all, because like the bike tire gauge just straight up shoots a piston out kind of thing. But what happens here is the gas comes in at the bottom and it actually tries to straighten out the metal. It's got spring to it, so as the pressure increases, this thing will straighten out. Not like this does, but it'll straighten out some, and then it's tied to a little bit of a lever mechanism which turns the needle on the outside so you can measure what the pressure is. And then how stiff this is or how this is geared determines like what pressure ranges it shows on the gauge. But what a gauge pressure is and how it's different than like a barometer reading is a gauge pressure is not absolute pressure, but it's the pressure above atmospheric pressure. So in fact, the manometer, this pressure that you're measuring here is pressure above atmospheric pressure, so it's more closely related to what you see in a gauge. I've replicated this chart of units over here, and I also sort of have a few words down here if you look at the slides closely. It tells you how a torr and a millimeter mercury are slightly different from each other. But the difference is so slight that most people don't worry about the difference. So I wanted to show you some pressure conversions between different units of pressure, and it's the same process that you go through using dimensional analysis to convert any other unit. So for example, if you want to convert 1.25 atmospheres to millimeters of mercury, then you want your pressure in millimeters of mercury, right? Start with the 1.25 ATM, then look up the appropriate unit conversion, right? So it's 760 millimeters of mercury for every 1 atmosphere. And you'll end up with 950 millimeters of mercury after you cancel out your atmospheres. Now that's the 760 is almost exact. It has way more sig figs than anything else on this table, actually. And the 1 atmosphere is also exact. So the units, the sig figs, will be determined by the numbers in the original given number. And so this number should really be expressed as 9.50 times 10 to the 2 millimeters of mercury. Now, a slightly more difficult conversion is I have inches of mercury and I want to do kilopascals. And the reason we do kilopascals is, since an atmosphere basically equals so many pascals, you end up with usually, and when you convert to pascals, really large numbers, and kilopascals is just a better way to express the unit. So we want to do kPa. And if you look over here on the right hand side, right, I have inches of mercury down here, and up here I have pascals. So my relationship is 29.92 inches is equal to 101,325 pascals. So I can go from inches of mercury to pascals, and then it's one more step to go to kilopascals, kPas, like that, okay? And the conversion is perhaps what you're thinking it would be. 1 kPa is equal to 10 to the third pascals, like that. So let's go ahead and do that. We want to get 17.5 inches of mercury into kPas. And so our first step is to do this. It's 29.92. I just realized I left the mercury off over here. 29.92 inches of mercury for every 101,325 pascals. And then one more step is I want pascals to cancel at the bottom, and I'll be left with kPa like this. And so this is 10 to the third pascals at the bottom. And when you do that calculation, you get 59.264 kPa, or 3 sig figs in the number that's given, so 559.3 kPa, like that. Okay. So again, pretty similar to all the other conversions, just a couple of different new conversion factors. And you also have to be aware that typically pressures would be exhibited in kilopascals rather than just straight pascals. But that's a conversion for that.